Good morning everyone. In the last lecture, we have discussed linear programming problem by taking the example of maximization of profit, where we considered the example of 2 decision variables and 3 decision variables as well, especially by using Simplex method. Today we will consider the minimization problem. See, in order to solve the minimization problem by using the Simplex method, we will first convert the minimization problem into a maximization problem. Then we will solve the linear programming problem by using as usual procedures of the Simplex method. So, the first step toward solving linear programming problem by using the Simplex method that we are already discussed, that we want to constitute the standard form, which is the baseline format for all linear programming problem. So, the standard form is necessary because it creates an ideal starting point for solving the Simplex method as efficiently as possible. So, of course, for formulating the standard form of a linear programming problem, first we have to consider the decision variable along with the objective function. So, objective function may be maximization or minimization problems, but in this particular class, we are going to consider the example of a minimization problem. So, our objective function will be the minimization. Then we are going to identify all the constraints and which we are denoting in terms of inequality forms. So, here it will be greater than or equal to sign here because we have a minimization problem. See, after specifying our objective function and converting in the form of inequality, then next one is all the variables that should be non-negative. That means we have to specify that all our decision variables are positive or it is equal to 0 or it may be greater than 0. So, after formulating the standard form, see here we are going to consider one example. See, consider the example of a minimization problem. That is, we want to minimize, that is cost is equal to 3x1 plus 2x2. So, here our objective function is specified, that is the minimization of cost. See, after specifying our objective function, the next step is to identify what are our various constraints. So, here our minimization problem is subjected to the constraint of 2x1 plus x2, which is greater than or equal to 6, because the standard format of the minimization of problem, that is greater than equal to 6. So, here then the second constraint, that is x1 plus x2, which is greater than equal to 4. Then here we are also specifying, that is the variables x1 and x2 which is greater than or equal to 0. So, we have a minimization problem here, and here we are going to convert the minimization problem into the maximization problem. So, for that particular case, we are going to consider the dual of the minimization problem. We know how to find or how to formulate the dual, especially from the given primal problem. See, this particular minimization of cost problem is considered as the primal problem. Now, we are going to find its dual. So, for that, first we know the objective function in the primal is minimization, then our dual will be maximization. So, here I am going to specify our objective, that is the dual problem, that is maximization of Z, that is maximization of profit here. Then the column vector of the constant from the primal constraint now transposed to the row vector coefficient for the objective function in the dual. That means here the column vector of the constant, that is 6 and 4, that will become the coefficient for our objective function. In the earlier case, that is in the primal problem, our decision variables were x1 and x2. Now we are going to replace this x1 and x2 by using y1 and y2. So, here 6y1, see the coefficient of the objective function that is taken from here, that is column vector of the constant in the primal constraint, that is transposed to the row vector for the coefficient of the objective function. So, here it is 6y1 plus 4y2. Now, after that the inequality sign of the technical constraint are reversed. That is greater than equal to, now it will become less than equal to. That we will also want to establish. Along with that, non-negativity constraint of the variable that are to be maintained. So here it will become the dual problem which is subjected to the constraint, that is by taking the transpose of the variable, that is 2, 1, that now we are going to consider in the form of column, and 1 will be considered for the second column. So it will become 2y1 plus y2 which is less than or equal to, see it is greater than equal to in the primal problem. Now we are converting into the less than equal to, see the coefficient of the objective function in the primal problem will become the constant of the constraint in the dual problem. So 3 and 2 now will become here the constant of the constraint here. So the constraints will become 2y1 plus y2 which is less than equal to 3, y1 plus y2 which is less than equal to 2. Now we have two decision variable here, that is y1 and y2, and these two decision variable are assumed to be greater than or equal to 0, that is the decision variable must be positive. So in this way we can find the dual of the given primal problem. So the primal problem was the minimization of cost, which we are converted in the dual problem, that is maximization of the profit, which is the 6y1 plus 4y2. Now by using its dual, that is maximization of profit, now we are going to solve this linear programming problem by using the simplex method. So we are specified our standard form, then we are going to determine the slack variables. So the second step, that is to convert the given linear inequality constraints into the linear equation by adding or by introducing the slack variables. So of course we know the slack variables are the additional variable that are introduced to transform them, especially from the inequality constraint into the equality one. So thus we are adding here slack variables into the concerned equation with the coefficient 1, and at same time the slack variables of the other equations are given the coefficient of 0. So in our example, see this is our original dual problem which we are formulated here. Then here it will become the first constraint we are going to write by introducing the slack variables, that is 2y1 plus y2, then introducing the slack variable s1 and s2, because we have two constraints here, so we have two slack variables as well. So it is s1 and s2 we are adding here by providing coefficient 1 for s1, that is for the first constraint, and by assuming 0 for the second slack variable, so that it is 0 s2, and converting this inequality sign into the equality sign, so it is equal to 3. Similarly, the second constraint, that is y1 y2 which is less than equal to 2, it will become y1 plus y2 0 s1 plus s2. So coefficient here it will become s2 will become 1, which is equal to converting the inequality sign into the equality, so it will become 2. Now after that we are considering the maximization objective, that is z is equal to 6y1 plus 4y2. Again we are going to converting this particular objective function by adding the slack variable and taking the 6y1 plus 4y2 into the left side, so it will become minus 6y1 minus 4y2 plus 0s1 plus 0s2 plus c, which is equal to 0. After introducing the slack variables to convert the inequality constraint into the equality constraint, we are going to set up a simplex tableau that is actually representing the linear programming problem and which is used for checking the optimality or optimal solution. So as a simplex tableau which is used to perform row operations on the linear programming, as well as which is used to check the optimality solution. So the table is here organizes in such a way that the coefficient of the decision variable, the slack variables, along with the coefficient of the objective function, which we are going to write in a tabular format. So I am introducing here, that is simplex tableau, by using our problem. So here I am introducing the table by taking the two variable. We have a two decision variable here, that is y1 and y2. So y1 y2 is taken here, then s1 s2 we have two slack variable, then we have a constant in the constraint, that is b. So see in the given tableau, the bolded top row, that is the tableau states that each column what it represents. And here the following two rows, these two rows will be representing for the two linear constraint variable coefficient from the linear programming, and the last row will be considering the objective function coefficient. So I am going to write the coefficient of the constraint and the objective function in the given Simplex tableau, so that it will become, see, it is 2110, and then constant, that is 3 here, that is putting in the column of B. Then the second constraint, that is the coefficient here y1, y2 1, 0, then S2 for 1. So here putting here again the constant is equal to 2. Then we are considering the objective coefficients. See here it is -6, -4, 0, 0, and then we are B constant is also equal to 0. So after setting up this particular table, then it is ready for checking the optimal solution. So here checking the given solution is optimal or not. How we are going to find it? See, all the values in the last row, that means the objective row, the coefficient are non-negative. That means it contain certain greater than or equal to 0 values in the case of a maximization problem. So if the value is less than 0, that means if the value is negative in the bottom row, it means that the solution is not reaching in the optimal value. So if it is not optimal, then the current solution can be improved, and the Simplex method proceeds, the pivoting towards the better solution. So we are going to check our given Simplex tableau is optimal or not. So from especially our example, see, this is the Simplex table, and here we are going to check the last row, that is objective row. So which is here -6, -4, 0, 0, 0. So we have two negative values exist in the bottom row, which indicating that this solution is not an optimal solution. So if our tableau is not optimal, then the next step is to identify pivot variable or pivot element through the interactive process to create a new table. So first here we are going to identify pivot row. So especially for that we are going to conduct the interactive process. So if our current solution is not optimal, then we want to improve the current solution, and to improve the current solution we are bringing new basic variables into the solution. We can call this is an entering variable, and when the variable is enter, then another variable will be leave from the particular system. So we can call this is a departing variable. So here the entering variable considered as the pivot column, smallest negative value in the bottom row. This will be the entering variable, and at the same time our departing variable will be it is the pivot row. For that we are going to calculate the test ratio, and among the test ratio values we are going to consider smallest non-negative value. After finding out the pivot column and pivot row, we will find the pivot element, that is nothing but it is the intersection value of pivot row and pivot column. So now we are going to do all this exercise so that it will be more clear. See, in our example, see the table from the bottom row, the tableau, which is the new coefficient in the objective function. Pick the smallest negative value in the bottom row. So here it will be -6. So this column can be marked as a pivot column, and once pivot column is fixed, then the next one is to find out the pivot row. So here I am marking the pivot column. Then for finding out the pivot row, we are going to consider the B value. B value we are going to divide by using the pivot column elements. So here it will become, see the test ratio, it will become 3 by 2. It will be 3 by 2, and another one is 2 by 1. 2 by 1 which is equal to 2. So here we can say that after dividing or after finding the test ratio, the smallest positive value here it is 3 by 2, and this 3 by 2 is corresponding to the first row in the given tableau. So the first row will be considered as the pivot row, and I am marking here by using the red color. So the value that is smallest non-negative value in the test ratio, that is here it is 3 by 2, will become our pivot row. So after finding the pivot row and the pivot column, the next step is to find out the pivot element, which is the value at the intersection of the pivot row and the pivot column. which is marked as a pivot element. So here it will become, see, 2 will become the pivot element. So because it is the intersection of the pivot column and the pivot row. So here the pivot column will be the entering variable in this case, and pivot row will be considered as the, it is replacing, that means it is departing variable. So now we are going to pivot the entire table and going to find out new values for the instead of old values. So first we are going to consider, pivot row and going to replace the old values by using new values. So we are going to calculate the new values for the pivot row. So by using the equation, that is, we are going to multiply each element of the pivot row by using the reciprocal of the pivot element. So the reciprocal of the pivot element here, it is 1 by 2. So by taking the first element, that is 2 into 1 by 2, which is equal to 1. Then 1 into 1 by 2, which is equal to 1 by 2. Again 1 into 1 by 2, it is again come out with 1 by 2. Then the next element is 0, that is 0 into 1 by 2, which is equal to 0. Then 3 into 1 by 2, which is equal to 3 by 2. Now we are going to replace the old element in the pivot row by using the new calculated values. So the pivot row will become, see, 1, 1 by 2, 1 by 2, 0, 3 by 2. Okay. Now after calculating the values for the new pivot row, now we are going to consider the second row. Second row we are going to replace by using new values. For that we have to use the formula, that is old value minus corresponding value in the pivot column into new value in the pivot row. So here for the second row, first element is 1. So old value is 1 minus corresponding value in the pivot column, which is also here it is equal to 1. Then multiplied by new value in the pivot row. So what is the new value in the pivot row here? It is equal to corresponding old value, it is new value in the pivot row is equal to 1. So here it will become 1 minus the corresponding value in the pivot column, which is equal to 1. So 1 minus 1 into 1, which is equal to 0. Similarly here the second element, that is 1 minus 1 into 1 by 2, which is equal to 1 by 2. Then 0 minus 1 into 1 by 2, which is equal to again minus 1 by 2. Then we have 1 minus 1 into 0, which is equal to 1. Then 2 minus 1 into 3 by 2, which is equal to 1 by 2. So the second row, we are calculated the new values. We are going to replace the old values by using the new calculated value. So it will become, see, 0, 1 by 2, minus 1 by 2, 1, 1 by 2. Okay. Now we have the last row, that is the objective row. Again the value for the objective row, again we are going to replace by using new calculated value. For that we can use the formula, that is the old value minus corresponding value in pivot column into new value in the pivot row. So here it will become old value, which is equal to minus 6, then minus corresponding value in the pivot column, which is also minus 6, then into new value in the pivot row, which is equal to 1. So I am writing here, that is minus 6 minus then corresponding value in the pivot row, which is equal to again minus 6 into new value, which is equal to 1. So minus 6 minus minus 6 into 1, which is equal to 0. Similarly, the second value, that is minus 4 minus minus 6 into 1 by 2, which is equal to minus 1. Then we have 0 minus minus 6 into 1 by 2, which is equal to 3. Then we have 0 minus minus 6 into 0, which is equal to 0. Then again 0 minus 6 minus minus 6 into 3 by 2, which is equal to 9. So now we are going to replace all the values for the objective row by using new calculated value. So it will become 0, minus 1, 3, 0 and 9. So here we have new table is arrived. So in this particular case, we are going to consider the departing variable and entering variable. So here the departing variable is corresponding to the smallest non-negative ratio, that is considering the pivot column, and corresponding to the pivot column our entering variable will be, it will become y1. What is the departing variable here? Corresponding to the variable to the pivot row, that is the first row, here we have basic variable which is S1, which will be one of the departing variable. So here we are going to replace S1 by using the entering variable, that is Y1. So it will become, see, instead of S1 I am going to write it is Y1. So after doing all this exercise, now the table is ready for the optimality check. That is, check whether the given solution is optimal or not. See, in the given table, if all the values in the bottom row are the positive or equal to 0, then we can say that we have an optimal solution. But here we have one value that is -1. Still we have a one negative value exist in the bottom row, indicating that this particular solution is not an optimal solution. Then we are going for, again the process of pivoting by identifying pivoting element through the interactive process to create a new table. So here we are going to again conduct all the process through the process of pivoting. So here we have the new table is ready for interactive process. Now here we are going to consider the smallest negative value, which is equal to -1 here. So -1 corresponding column will become pivot column. So I am highlighting here, this is the pivot column here. Then after finding the pivot column, we are going to find out the pivot row. For that we are going to calculate the test ratio. So the test ratio we can calculate it by dividing the B by using the corresponding values in the pivot column. So it will become, see, 3 by 2 divided by 1 by 2. So by using the cross multiplication it will become 3. Similarly, the second test ratio, that is 1 by 2 divided by 1 by 2, which is equal to 1. So here the smallest non-negative value, that is equal to 1 here. So corresponding to the 1, we have a row which is considered as the pivot row. So which belongs to the second row. So the second row will be considered as the pivot row now. So we have the pivot column as well as the pivot row. Now we are going to find out pivot element. So here the pivot element is considered as the intersection of the pivot column and the pivot row. So 1 by 2 will become the pivot element here. So after identifying the pivot element, we are going to consider the replacing the pivot old values by using new value. So here how we will get a new value? We have a formula for that. That is, we are going to multiply each value or each element in this given simplex tableau by using the reciprocal of the pivot element. So reciprocal of the pivot element, it will become 2 by 1, which is equal to 2. So here I am going to multiply each value in the pivot row by using 2. So it will become, see, 0 into 2, which is equal to 0, 1 by 2 into 2, which is equal to 1, then -1 by 2 into 2, which is equal to -1, then 1 into 2, which is equal to 2, then 1 by 2 into 2, which is equal to 1. Now I am going to replace the old values in the pivot row by using new calculated values here. Therefore, the pivot row will become, see, now it is 0, 1, -1, 2, 1. Okay. So this is now the new values for the pivot row. See, after finding the pivot row, now we are going to replace the old values of the first row by calculating the new value. So how we are going to calculate here? See, the old value minus corresponding value in the pivot column into new value in the pivot row. So here it will become, see, the old value, that is 1, minus then corresponding value in the pivot column, which is equal to 1 by 2, into new value in the pivot row, which is equal to 0. So it will become 1 minus 1 by 2 into 0, which is equal to 1. Then similarly, the second value, that is 1 by 2 minus 1 by 2 into 1, which is equal to 0. Then the third one, that is 1 by 2 minus 1 by 2 into minus 1, which is equal to 1. Then 0 minus 1 by 2 into 2, which is equal to minus 1. Then 3 by 2 minus 1 by 2 into 1, which is equal to 1. So now the old values of the first row we are going to replace by using the calculated new values. So the first row will become, see, 1, 0, 1, minus 1, 1. Okay. Now we have the last row, that is the objective row here. We are going to calculate the new value for the objective row by using the formula, that is the old value minus corresponding value in the pivot column into new value in the pivot row. So here the old value, which is equal to 0, minus corresponding value in the pivot column, which is equal to minus 1. Then new value in the pivot row, which is equal to 0. So it will become 0 minus minus 1 into 0, which is equal to 0. Similarly, the second element, that is minus 1 minus minus 1 into 1, which is equal to 0. Then the third element, that is 3 minus minus 1 into minus 1, which is equal to 2. Then 0 minus minus 1 into 2, which is equal to 2. Then 9 minus minus 1 into 1, which is equal to 10. So the last row, that is objective row, again we are going to replace by using this new calculated value. So it will become 0, 0, 2, 2 and 10. So once all the elements or all the values of the new table are calculated, now we are replacing the departing variable by using the entering variable. So entering variable here, it is corresponding to the pivot column. What is the variable here? It is y2. We are going to consider y2 is an entering variable. What is the departing variable here? Corresponding to the pivot row, that is here we have the basic variable, that is s2, and this s2 we are going to replace by using the entering variable, that is y2. So this table will become, see, s2 can be replaced by using y2. Now see the given table. If all the values in the bottom row are positive or equal to 0, then we can have a optimal solution. So this table is actually ready for the optimality check. Here, yes, all the new values in the bottom row or the objective row are positive or equal to 0. See, here we have 0, 0, 2, 2 and 10. So we can say that new values in the bottom row are the positive or it is equal to 0, indicating that we have an optimal solution. So ultimately we reached the optimal solution through the process of interaction. So from this final simplex table, see, the maximum value of z is equal to, it is 10. It is the maximum value. So of course we don't have any negative values in the bottom row. This is the optimal solution. The maximum value for the z, which is equal to, here it is 10. So at this particular 10, the value of y1 is equal to 1 and value of y2 is equal to 1. So since the maximization value of z is equal to 10, the solution for the original problem, original problem was, it is minimization of cost, and then we are converted this minimization cost problem into the maximization of profit problem. So here the maximization problem, the z value, that is maximum value, is equal to 10, and this 10 is also considered as the solution for the original problem, that is minimization problem, that is c is equal to, it is also 10. Why? Because one of the most important property while we were discussing about the duality is that the optimal value of the primal objective is also equal to the optimum value to the corresponding dual objective function. So here the duality here, see, the original function we have the 10, that is value of z is equal to 10, therefore the corresponding dual is also having the same value, that is optimizing value is equal to 10. But the variable here y1 is equal to 1, y2 is equal to 1. But we want to find out the x1 and x2, because x1 and x2 is actual value for the our minimization problem. So here the x1 and x2 will become instead of corresponding to the value, that is s1 and s2, which will become the value of x1 and x2. So here the minimization problem's solution is found under the slack variable, that is yielding x1 which is equal to 2 and x2 is equal to 2. So corresponding to this particular variable, that is s1 and s2, we have x1 and x2. So here x1 is equal to 2 and x2 is equal to 2, and c is equal to, our objective function was original function, primal problem, that is 3x1 plus 2x2. So here substituting the value of x1 and x2 in the given original function, that is minimization problem, so it will become 3 into 2, that is x1 is equal to 2 and 2 into 2, that is x2 is also equal to 2. So 3 into 2 plus 2 into 2, which is equal to 10. So which is also matching with here our problem, which we are ultimately reached to the an optimal solution, which is also equal to 0. So we have an optimal solution for the original minimization problem by converting the primal problem into the dual problem. So in this way, we can find the solution to the linear programming problem with minimization of cost by using the simplex method. We are converted the minimization problem into the maximization problem, and accordingly we reached to the optimal solution. So I am concluding here. I hope you understood whatever the exercise which we done here, it is clear to you. So thank you.